Hello everyone. We're going to actually start a new topic now. We're going to start studying how we can analyze functions that make multiple recursive calls. The one we're going to start with is going to be computing the Fibonacci numbers. I will briefly explain what they are for anybody that's never seen them before. The Fibonacci numbers are a sequence of numbers where each number is the sum of the two previous ones. There are two starting seeds, 1 and 1, and then the next number is the sum of those two. So 1 plus 1 gives us 2. The next number is the sum of the previous two. So 1 plus 2 is 3. The next number is the sum of the previous two. So 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, and we would keep going. This is a good example of a recursive function that requires multiple recursive calls because we need to have the two previous values. We're going to need to have the two previous values for our recursive calls. We have the code for computing it over here. There's a couple of bits of information in this code. The first is we want to identify the base case, which is hiding in this if-then statement here. This says that t of 1 is equal to c. Or you could even say t of 0 is equal to c. Both are okay. We then have two recursive calls. A recursive call of size n minus 1. So we have a t of n minus 1 there. And we have a recursive call of n minus 2 as well. And then we have some other code that takes constant time to return and add those two numbers together. So the complexity of this function, t of n, is given by t of n minus 1 plus t of n minus 2 plus c. If we want to analyze this function, it actually proves to be very difficult to use our substitution method. We get what might be called a combinatorial explosion if we were to keep trying to do the substitution method. If you want to make yourself suffer a little bit, you can bother trying to go down that rabbit hole. I do not encourage it, though. So instead, we are going to have to bound this. So I'm going to write that down as like a rule of thumb. When we have multiple distinct recursive calls we must bound the recurrence. There is almost never any way around this. We will see one other technique where we can get around this, but I'm going to box this in and even put a little star next to it to let us know that that is effectively a golden rule for these problems. For this problem, we're actually going to start by bounding it below. So we're going to bound below. The way we're going to do this is we're going to try to look at the two recursive calls that we're making and identify the larger of the two. What do I mean by that? First, let's copy down the function here. We have this for our function. We want to understand which of those two recursive calls, t of n minus 1 or t of n minus 2, is bigger. T of n represents the runtime as a function of n. If we are trying to identify which one is bigger, a bigger value being plugged in would result in a bigger value as an output. So the larger of the two, of t of n minus 1 and t of n minus 2, this term, t of n minus 1, is the largest, or larger. And the second term, which we'll underline in purple, this term is smaller. So if we're trying to bound this below, our trick is going to be that t of n is greater than or equal to, if I take the larger of the two terms, the green one, and replace it with the smaller of the two terms, the purple one, then I will definitely make it smaller. So if I replace t of n minus 1 with t of n minus 2, then we definitely make it smaller. Let me group together my like terms. So we have t of n greater than or equal to 2 t of n minus 2 plus c. We've actually seen something look like this before, so I'm actually going to even further bound this below by getting rid of the plus c. And we'll see why when we keep analyzing this. So if I drop the plus c, I again make it smaller. We then are going to solve this with substitution. So we're going to plug n minus 2 into that equation, which maybe we designate with something. I use the blue dash here. So we're going to plug n minus 2 into the blue dashed equation. Doing so, we have t of n minus 2 on the left-hand side is greater than or equal to 2 t of n minus 2 minus 2, which is n minus 4. We're then going to substitute that into the equation. So we get t of n greater than or equal to 2 times make the substitution, and we get 2t of n minus 2. Distribute the 2 quick, and we have t of n greater than or equal to 4. Sorry, this should be a t of n minus 4 here. I apologize. 4 t of n minus 4. We then make another substitution and plug n minus 4 into the blue barred equation. Doing so, we have t of n minus 4 is greater than or equal to 2, t of n minus 4 minus 2, which is n minus 6. Then plug that into the equation that we've written in green, and we have t of n greater than or equal to 4 times make the substitution. We have 2t of n minus 6 there. Distribute the 4, and we have t of n greater than or equal to 8, t of n minus 6. And now we need to only identify a pattern. So the coefficients look easy. We have 8 for this equation, 4 for the one above, and 2 for the original. Those are powers of 2. So this term looks like 2 to the k. The t of n minus term looks like t of n minus 6, t of n minus 4, t of n minus 2. That's multiples of 2. So that looks like t of n minus 2 times k. So for any value of k, we have t of n is greater than or equal to 2 to the k times t of n minus 2 times k. We then want to try to use our base case. So we know that this stops when the thing inside of t, which in this case is n minus 2k, is equal to our base case. What's our base case? If we scroll way up to the top, our base case was 1. So n minus 2k equals 1. Solve that for k. Skipping the algebra, that gives us k equals n minus 1 all over 2. Substitute that into our expression here, and we have t of n is greater than or equal to 2 to the plug-in k, and we have n minus 1 over 2, times t of n minus 2k is equal to 1, and t of 1 is equal to c. So t of n is greater than or equal to, I'm going to rewrite the first term just to make this really obvious. I can write that as 2 to the n over 2 times 2 to the negative 1 over 2 times c. Let's clean that up a little bit. So that's some constant, c times 2 to the negative 1/2 times 2 to the n over 2. So, therefore, t of n is in big omega of 2 to the n over 2, which is a sufficient answer for this problem because that is an exponential lower bound. Exponential lower bound. Therefore, we are done with the problem. So, for this, we don't need to bound it above. We will see examples in the future where we have to bound these above. But for now, we are done with this problem and don't need to do anything more. I will quickly mention that problems of this form, we can typically expect this. We have two recursive calls that look like t of n minus something. You should always start by bounding these below because you can expect it to give you an exponential lower bound. So keep that in mind in the future. But that's it for our first example. We do not need to do anything else.